Let's learn about surface integrals. Let me first remind you about something we learned very early in the semester. If you have a parallelogram defined by two vectors, the magnitude of their cross product gives you the area of the parallelogram. We're going to be using that pretty soon. Let me remind you of something else. If you have a trajectory in space defined by r of t, you may recall that the derivative of r with respect to arc length gives you the unit tangent vector in the direction of motion. So this is also telling you that if you take dr, that is just the unit tangent vector times the differential of arc length ds. So if you were looking over here at dr, where this is like a tiny little vector, its length is ds, because this is a unit vector and doesn't contribute to the length. Why does that matter? Well, let's talk about a more general case where we have some kind of surface flopping around in 3D space with a coordinate system of some sort, x, y, z. And let's suppose this is defined not in terms of t, but in terms of two parameters, u and v, where, for instance, let's say that u is in this direction, and let's say that v is in this direction. So that if you look at the lines where v is constant, where u is constant, and you look at the lines where v is constant, you're creating a kind of grid on this surface in space. These are your parameters, two parameters for a two-dimensional surface. And if you look at this guy right here, and you'd like to know what that little bit of area is, well, this side, where u is changing and v is constant, this little patch will have partial r, partial u, du, for its little vector on the side, and this other guy on this side, where v is changing and u is held constant, will have length partial r, partial v, dv. And is this really a parallelogram? No, it's not really a parallelogram, but it'll be an approximate parallelogram. And if you're doing this for a very small measure, if you have a fine mesh on this, it'll be pretty close. And so we end up looking at ds, this little patch of area ds. It's going to be the magnitude of the cross product of these two little vectors. Now keep in mind, du and dv, just scalars. I'm going to factor them out, and we're going to have r, u cross r, v, where I'm using subscript notation for partial differentiation because it's more convenient. What does this mean? Well, here comes a flashback. Let's suppose that our parameterization up here is very simple. Suppose that we're just using x and y for our parameters in the usual way, and that z is a function of x and y. So my parameterization of the surface would be x, y, f of x, y. I've certainly seen that before. Now what happens if we find r sub x? Well, that's going to be 1, 0, f sub x. And what's r sub y? R sub y will be 0, 1, f sub y. If we now cross these, what is going to happen? going to have Rx cross Ry set up Rij k. All right. And we're going to have 1, 0 fx and 0, 1 fy. We do the cross product. We're first going to get, let's see, minus fx. We're going to have an extra minus here. We're going to have minus fy, and we get 1. If we take the magnitude of Rx cross Ry, we're simply going to have the square root of fx squared, fy squared, 1 squared. And so if ds is Rx cross Ry, take the magnitude, dx and dy, we just found out that we got this. Fx squared plus fy squared plus 1 squared, and we have dx and dy, which we've seen before. In fact, we saw that in the previous chapter when we were talking about surface area. So that's a bit of a letdown and nothing new. Remember, surface area is just the integral over some domain of 1 ds, or the integral over some domain of fx squared plus fy squared plus 1 dx dy. Not interesting. But wait a minute. If we have a more general way of doing this now with Ru and Rv, where we don't have to depend just on x and y, then we can parameterize all kinds of surfaces, and instead of simply talking about surface area, we could replace this with whatever we like. If we put in a density function, we would be getting the mass of our surface area, like a lamina in space. Could be any shape at all. Let's do a very specific example. Here's our friend, the right circular cone. Now, you know, if you use similar triangles, you go up a distance z and out a distance r. R will be to A as z is to h. So h over AR is what z is equal to. That's kind of handy. There's something else we know. Anytime you want to talk about a position vector in space, it's xyz. I mean, that's always true. Now, if you can parameterize this, let's use cylindrical coordinates. That would be r cosine theta, r sine theta, and z. But we know something interesting about z. We can write this as r of r and theta, r cosine theta, r sine theta, h over r over a. H times r over a. So what's r sub r? I apologize for using two versions of r, but I hope you can handle that. Well, it's just cosine theta. It's just sine theta. And it's h over a. What's r sub theta? Well, that's minus r sine theta, r cosine theta, and this one is going to be 0. Let's cross these guys and see what we get. So here we go, crossing r sub r with r sub theta. Okay, we need a little room for this one. In the middle, we're going to have cosine theta, sine theta, h over a. Down at the bottom, we're going to have r sine theta, r cosine theta, and 0. And of course, let's finish this off. Our ijk, put it at the top, left it to last so the spacing would be a little easier. Okay, so here goes. We're about to do our computation now. And when we're doing the cross product, the first thing we get is for I, we get 0 minus HR over A cosine theta. Okay? And then we get a minus sign on the J term, 0. This minus would cancel. Okay? And so what would happen would be it would go away, but we have an extra minus, so we still have a minus. We have HR over A sine theta. And for this one, for the last component, we're going to get R cosine squared theta. Okay, this minus does cancel. We get plus R sine squared theta. In other words, minus HR over A cosine theta minus HR over A sine theta and plain old R. Okay? So that's our result from our cross product. And now that we've gotten this far, let's see what's going to happen next. We need to find the magnitude. Okay, so when we're finding the magnitude, we do a bunch of squaring, right? So we're going to have a bracket here, h squared r squared over a squared cosine squared theta plus h squared r squared over a squared sine squared theta plus r squared, and this will all be to the 1/2 power because we have to take a square root. Cosine squared, sine squared, we simply have h squared r squared over a squared plus r squared. Okay? If you want to put this over a common denominator, which for some reason I want to do right now, I have h squared r squared plus a squared r squared all over a squared. And I can factor out an r from the top because there's an r squared. I can factor out an r and I can factor out an a. R over a h squared plus a squared. Now you know what this is. A squared plus h squared, if you go back to our cone, that's just the diagonal length here. That's the slant height, a squared plus h squared. And it's a constant. We just found out that ds for the cone is r over a square root of a squared plus h squared. And our differentials are dr and d theta. Now we can integrate anything we like over the surface of the cone by using this information. And I'm going to post a couple of examples for you to fill in details. But for example, if you wanted IZ, you would just integrate over the cone and you would use r squared, r over a, square root a squared plus h squared, dr d theta. And that would work it for you.